Example 6.13 from Chapter 6 of OpenStack's Let's Rank Ionization Energies. Ionization energy is the energy required to remove the outermost electron from an atom or a molecule. So here we go with the first one here is the first ionization energy. That's what that means. IE1 is the first ionization energy for aluminum. Aluminum has, it's right there, it has 3 valence electrons, being in group 13. So just take the second digit, and that's your valence electrons of that group number. And because it has, well, here's the 3s orbital, that's full there, and then the 3p sublevel, it's only going to have 1 electron there. So that electron is not going to be too stubborn about staying there. It's going to come off pretty easily. That's what the first ionization energy is. The first ionization energy for thallium, let's scroll down the periodic table, it's in the same group, so that's going to make it nice and easy to compare. That also looks just like, or not just like that, but it looks something like that. It has 3 valence electrons. That's got a ton of other stuff going on underneath it, but that's what we want to compare. Let's go with this one here. Sodium. The second ion is, oh, that's careful here. That's the second ionization energy for sodium. That looks like that's going to be tough to do because sodium will lose its 1 valence electron. So sodium has 1 valence electron, and a ground state sodium atom has 1 valence electron right there. But once that one's going to come off pretty easily. But that too means the next one under is a core electron. That's not going to come off easily at all. That's going to require the most energy out of the 3, I'll tell you right now. Let me go a different shade of blue for this aluminum again. The third electron. All right, so after the first, after that one leaves, how much energy to remove that third and final one? That's not going to be too bad either because it's still a valence electron. Well, the easiest one is going to be thallium because, so that is going to require the least amount of energy. Look at this. N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, N equals 6. That valence electron right there is in the 6p orbital. It's so far away from the center of attraction is even though it has 81 protons, it's also got 81 electrons. And a lot of them are shielding that, and those ones on the outside. Thallium is 1, 2. I got to draw this out. Make it 1, 2, 3. Now this is definitely not drawn to scale. 4, 5, 6. All right, that baby right there in the 6p. That's the 6p1 electron. Is all by itself. Well, it's actually got 2 other ones on along with it there. In the 6, these are your 6p. I'm sorry, 6s2, and these are your 2 electrons. But those 3 electrons are all, and you know they can be anywhere in here. It's a cloud of probability. But to answer this baby's all the way out there. It's like, you want me to leave? I'll leave. It's not going to be very stubborn. So that is going to be the easiest. It's not going to require a lot of energy to remove. Thallium has the lowest ionization energy. Ionization energy from least to greatest. Now let's take a look at these other 2, or other 3 scenarios, all in the same period. Aluminum is going to be the next. Aluminum's first electron is going to be the next easiest to pull away because aluminum has 13 protons. Let's keep that in mind. And the electrons we're trying to pull away are the outermost electrons in the 3p. So there's the 3p1 electron, and then there's 2 other ones over there too, and they're kind of shielding a little bit. The s orbitals are, because they've got something called orbital penetration. But for more or less, they have that. Let me do the 2 aluminums here at the same time. The energy to remove that guy, all right, there's some amount of energy. It's clearly going to require more energy to remove aluminum's 3p1 electron than it is thallium's 6p electron. So we know that. So I'll put aluminums. Oh man. Ionization energy number 1 for aluminum. We know that's going to require the next lowest amount of energy. Because think about it, if we remove that guy, all right, and then we remove that guy, that's going to take a little more energy. Now this guy is going to take even more energy than the first two of its buddies left. Now, you might think, well, that's that's a lonely electron out there by itself. Right, but remember, every time you lose an electron, the remaining electrons feel more of an effective nuclear charge because that's not changing. There's 13 protons there all the time. That's what makes it aluminum. Once you pull one away, the remaining 12 are going to feel more of an attraction toward that center. And then you're taking another one away. So the effective nuclear charge is increased for this guy. It's going to require more energy. I think we did it in this color. All right, that one's going to require more energy because it has a greater, the Z effective is greater for that. For ionization energy for the third electron, right, is greater than for the ionization energy for the first electron. It's going to take more energy to remove the, that's true for any atom. Any subsequent electron is going to require more energy than the first one because of that reason. The greater effective nuclear charge. Ionization energy for number 3, the third electron for aluminum. And so we know the one that's going to require the most energy is going to be sodium. And let me go back to what I was saying earlier. Going to need more room. If it said sodium's first ionization energy, then that would have been a much harder question. But it says sodium's second ionization energy. Well, that makes it easy because sodium does not want to lose 2 electrons. It'll lose 1 electron, but it is not going to want to lose 2. So here's an energy diagram. Sodium has 11 protons. Here's your 1s. It's got 2 electrons there. Here's your 2s. Got 2 electrons there. Here's this 2p, and it's got that full 2. That's neon, by the way. And then it has this one valence. There's your valence electron. This baby is going to leave without much effort. So the ionization energy for that guy is not bad, but that's not what the problem's asking. Once this guy leaves, now you're trying to take away one of these guys. That's a noble gas. That's isoelectronic. That means it has the same electron configuration as a noble gas. And you know they're very, very inert. They're stable, especially neon. This thing is happy the way it is. After this guy leaves, the rest are really stable. Good luck trying to get one of these guys, but you can do that. That's going to require a lot more energy. Its orbitals are full of electrons, and it's harder to take those out. Ionization energy, number 2 for sodium, is going to take the most amount of energy. Now, and pause the video. I'll look this up on Google, and we'll see what the actual numbers are. Pause. All right, I'm back. I don't know how reliable this stuff is because the first thing I saw was Google's AI and spitting these numbers out. But for thallium is about 500 and, oh, wait a minute. That takes more energy. Oh, hold on. Let me go to another source and be back. I think it looked like Google was getting his information from like some homework.com, and I was like, okay, let me go to a little more reliable source like Wikipedia. No, I'm just kidding. But even Wikipedia says there's thallium it's right. It takes more energy. That's 589 kilojoules per mole versus aluminum, which is number 13. Now, I went to OpenStax, and it's just a bad problem because the reasons get beyond the scope of our class to explain this anomaly. All right, but I know they were expecting us to get the answer we got, which is here. But that's interesting. Like somebody can send a note to OpenStax. But this is the right answer in the solutions for OpenStax as well. Somebody just oversaw or overlooked this anomaly.